Now it's clear, I think. Okay, so we can wait 1 more minute. Okay, so a very good evening to all of you. My name is Mohit teacher, and this is all about me. I welcome you all on the YouTube channel of TEQIP GATE classes. Okay, and like yesterday and day before yesterday, we discussed about the abrasive jet machining operations. Okay, and today we are going to discuss about the ultrasonic machining. Okay, this is also one of the advanced or non-conventional machining operations, we can say. Okay, in which not only the matlab means not completely the mechanical energy we are using, but electrical energy is also using. Okay, so uh, okay, so as what we have discussed in the previous, like how we described all the previous processes, like same path we are following in this one as well. Like first we discussed about the principle, second we discussed about the working part. Next, then we will discuss about what are the process parameters, okay, about that. And next, after that, we will discuss about the material removal rate, okay, and how it is affected by the parameters that we are considering, okay. So let's start. Okay, so in USM is basically the ultrasonic machining process, and ultrasonic means whatever the frequency means, it's a kind of frequency. The frequency basically we are using in this process to provide the vibrations. Okay, and generally this frequency is it's considered to be like more than the audible range. What is like audible range, that is in the 15 to 16 kilohertz. So we are using greater than that. Like that is also there is also a range of that. So first of all, I'm just briefing that what is the concept. Okay, what is the principle is there, that like this is a tool. Okay, this is a tool. Okay, and this is basically the okay, this is the tool, and this is basically the horn. Okay, this is horn, and this is the workpiece. Now here we are using the system, like a simple like pump system, through which basically we are pumping the abrasive slurry over here. Now this abrasive slurry is like water plus the combination of it's basically the combination of water plus abrasive particles. Okay, good evening, Soumya, good to see you. So we are using the abrasive slurry here. Okay, we are putting the abrasive slurry. Okay, now this meaning of this abrasive slurry is we are using this abrasive particles. This is basically the combination of abrasive particles plus water. Okay, point 8 answer for homework. Yeah, Soumya, that I will today I will paste on that yesterday's that video. Okay. So abrasive slurry is basically the combination of abrasive particles plus water. Okay, means there is a one more term that is affiliated with the concentration. So that is concentration is basically affiliated with the water. Okay, so that we will discuss. That is not that much important, but if somewhere it is asked, then please keep in mind if they are talking about the content concentration, then it is affiliated with the fluid. So here we are using the water. Okay, so abrasive slurry is basically the combination of mixture of abrasive particles and the water. Now these abrasive slurry we are using over here. Okay, so abrasive particles, which is basically kept between the tool and the workpiece. Okay, initially this workpiece was here, but after some time when the machining is done, after that I'm using this figure. So these are basically the abrasive particles are there. Okay, and these are very small in shape that we had already discussed in the yesterday's process. Okay, so same like abrasive particles, that is made up of the aluminum oxide. Okay, silicon carbide. Okay, and the boron carbide also we can use over here. Okay, so that particles is mixed with the water, and we are flowing over in between the workpiece and the tool surface. Okay, now is this tool is connected with the horn. Okay, and this horn is connected with the transducers. Okay, now the function of the transducer is like just to provide the just to initiate the vibrations. Okay, so here basically okay, this is the horn and this is connected with the transducers. Okay, that also I will explain you in the that working part, but just to that how the vibration is created, that's what I'm using this one. So transducer is basically, the purpose of the transducer is to create the vibrations. Okay, and this good evening, Nilkant. Okay, so transducer is using to produce the vibrations, and this vibration is transferred to the horn. Okay, horn, we are why we are using the horn, that I will also explain you. So this horn is connected with the tool. Now this tool and the workpiece, in between that we are keeping these abrasive particles. Okay, now this abrasive particles is means is the vibration is connect is we are using the transducer, so that is creating the vibration. Okay, so as it is creating the vibrations, this is transferred to the tool, and the tool will also start vibrating. Okay, as the tool start vibrating, whatever the particles that is come in contact with the tool, that will also start vibrations. So it is like one particle has started vibrations, another will also start vibration, another will like that, it's like that. Okay, so this vibration motion is shifted from one to another one in layer by layer. Okay, in layer by layer. So whatever the particle that is in contact with the tool, or that is now in contact with the workpiece, both all these are started vibrating. Okay, so because of this vibration only, good evening, Avi. Just now we have started. Okay, so this because of these vibrations of these abrasive particles, the material will start removing from the workpiece surface. Okay, now you can. There is a one more thing you can see over here is like, if you will talk about is this tool will insert inside the workpiece surface. So whatever the gap, minimum gap is there, like this is the minimum gap. Okay, so this minimum gap will be throughout this cross section. Okay, so like we can say, like if we have to make a circular periphery, then we have to use the shape of the tool will be just circular, means just replica of that. Okay, so if we have to make the triangular over here, if we like for an example, if we have to make this kind of shapes, okay, on the workpiece surface, then the tool should be like this. Okay, means whatever the shape is required, accordingly we are using the tool, and in between them, in between that we are placing the abrasive slurry. Now why we are placing this abrasive slurry, that I will that I will tell you in the working part. Next slide. Okay, so here like yeah, this is what so is some of the notes that is required, so that's why I have written something. So machining process is applicable only for the brittle material. This process is not applicable for the ductile materials. The reason is like is the mechanism for the brittle material is like, is the abrasive particle is impinging, or just we are creating a vibrations. Okay, so because of the vibrations, the crack is initiated, and once the crack is initiated, it will propagate because of the continuous vibrations. Okay, because of the abrasive particles. Now if we are talking about the ductile material, then that is a softer material. Okay, so if it is a soft material, then whatever the abrasive particles is there. Now yesterday we discussed about the abrasive jet machining, in which the abrasive high velocity abrasive particles are coming impinging over the workpiece surface, and still we are considering that little bit amount of the indent, there is no proper shape is formed over the ductile material. Here it is not impingement, so that a high amplitude is inserted, it is just a vibration. So if it is a vibration, just think about of a rubber. Okay, that rubber eraser. Okay, so if you are impinging the if you are just keeping the abrasive particles on that, and just hammering, okay, hammering on that, so it will try to insert that, but that will not remove the material from the eraser. Okay, so that is basically the concept. So we are not using these this process is not applicable for the ductile material, it is only applicable for the brittle material. Please keep in mind this one. Okay, this one. Now the tool is ultra working at the ultrasonic frequency. So also you can keep like above the audible range of the frequency. So audible range is 15 to 16 kilohertz. Okay, so we are working above that. Okay, so that is in the range of 19 to 20 kilohertz. So This is the ultrasonic frequency we are using for this. Okay, generally it is range of it is range in the 920 to 25 in some of the books. Okay, kilohertz, and it can be like 19 to 25. That's not that big much variation. Okay, and because of whatever the abrasive particles that we are using, now size is same, because whatever the abrasive particles, if we are using of the alumina, then that is in the range of 10, 20, and 50, only 50 microns. Okay, that we have already discussed in the yesterday's day before yesterday lecture. Okay, for the abrasive jet machining. So here, like if we are talking about the how much amplitude is generated when there is a vibration is initiated, then it is in the range of 15 to 15 to 50 micron. Okay, over the workpiece. And one more thing is there, that this question can be raised, because this is the principal part. So this question can be raised, that if the material is removed from the workpiece area, then why the material is not removed from the tool side? Because yesterday we were talking about the abrasive jet machining, in which we are using the nozzle of the tungsten carbide, and it has a life of very less, like 20 to 30 hours. So here what kind of the tool we are using, so that there will be no removal of the material. Here please keep in mind that this tool is made up of the ductile material, but the softness is in our hand. Okay, मतलब आप इतना softness इतना मतलब जो that ductility should not be that much. Okay, so that please keep in mind. Okay, the tool we are using, that is a ductile, but the softness of that tool is not that much. Okay, please keep in mind this one. So whatever the vibration that is moves toward the tool side, that is absorbed. Okay, machining portion is flooded with the hard abrasive water slurry that I already discussed. Okay, now why we are using the slurry for that? There is a one more important thing, that like if you will use just the abrasive particles, okay, then what will happen? Whatever the material that will remove from the workpiece area, that will be floated in between the abrasive grains. Because like if you will see the abrasive particles, then it will be like this. If you will see the abrasive particles, then it will be like this. Okay, so what will happen, like there is a space is there, so whatever the material that has been removed from the workpiece area, or the workpiece cross section, so that will be inserted inside these particles. And this is like there is no bonding. These reds are basically the abrasive particles, so there is no bonding. These are just particle only, so they can move here and there anywhere. Okay, so whatever the material that has been removed, this black color is basically the material which is removed from the workpiece. So it can be floated, this material which is removed from the workpiece, that can be inserted inside this abrasive grains. So what will happen, if it will increase the volume in between the workpiece and the tool area. So how you will remove it? So you have to use the fluid. So either you can use the gas, but like is we have to make a good finishing process, so that that's why we are using the water, that is worked as a lubricant as well. Okay, because very small amplitude is means the removal of the material is in very small amplitude. That's why. Okay, so I think it's clear to you guys. Okay, once the frequency is applied, tool start vibrations, and abrasive particles indent over the workpiece surface. That I mentioned that this is the tool. So whatever the abrasive particle that is in contact with that tool start vibrating, and next to it, that will transfer the vibration. So like that it has happened. Okay. So because of that, the indentation cracks is initiate. Because crack is initiate, the reason is the ductile material, brittle material only we are using. Okay, so this is the crack is initiated, and once there is a regular continuous vibrations due to the other particles which is above that, so that will basically propagate that crack. Okay, so like that basically the brittle fracture is occurs. Okay, then the material is removed. The reason of the material removal rate is brittle fracture. Okay, the mechanism that is. Okay, so it's okay, I think. Okay, let's move to the working part. Working is like okay, here is basically we are using the pump. Okay, this is the container. Okay, and this is the water inside that, and this black is basically the abrasive particles. Here we are using the pump, and this is connected with the hoses. Okay, hoses like tubes we can say. So that will basically pump this abrasive slurry in between. Sorry, it's not here, it's here. This is a pump, and it will float this. It will supply the slurry, abrasive slurry over here. Okay, so this is basically the fixture. This is the anvil, this maroon color, this is the anvil, and this is the fixture over that we have mounted. Over the fixture, this is the workpiece. Okay, and this workpiece is over that. This is this light green section is basically the horn. Okay, this is the horn. Okay, and this section, this colored, is basically the transducers. Okay, transducers. Now this is connected with the high frequency power supply. Okay, and on the other hand, it is connected with the mechanism. So it is basically the feeding mechanism. This feed mechanism is like it will just try to lift it up and down. Okay, the reason is we have, what if, as we discussed, that it is the amplitude range, that vibrations that is created, the vibrations of the range of that vibration is very small, that is 15 to 50 micrometers. Okay, so whatever the particles is there, the vibration of the abrasive particle is very, very important. Okay, so now if what will happen, that if this is the workpiece right now, okay, and this is basically the horn. So if this is the minimum gap is required, so if abrasive particle is there, so that because of the vibration, that will remove the material. Okay, so now if this much amount of the material has been removed, then the distance is increased. The distance between the workpiece and the tool is, now the workpiece surface is this one. Okay, so this distance has been increased, so we have to maintain a constant distance, then only the material will remove from the workpiece area, because the vibration can be transferred to the workpiece. So what we have to do, we have to push it downward side. Okay, so now when you will push it, this will area will also come in contact with these boundaries, so that will also, the material will also be start removing from these areas. Okay, so please keep in mind this one. Now for the feeding mechanism towards the downward or the upward, we are using the servo motor. This is also the one of the important question has been asked many PSUs, that what mechanism we are using in USM. Okay, to for the feeding mechanism. Okay, so servo motor, servo mechanism we are using. Okay, for the feeding system, for the up and down. So okay, so what is the feeding mechanism we are using for the feed tool, feed motion? Okay, transducer used to generate the ultrasonic frequency. Yeah, that I already discussed in the principal part, that transducers we are using, and uh, that basically generating whatever the power supply that is coming through this high frequency, that is convert, this transducer is converted into the vibrations. Okay, now this transducer is basically like there are different types of the effect, like we can say that as a piezoelectric effect. Means this transducer can be work on different types of the mechanism, means different types of the effects. Okay, or the principle we can say. First is the piezoelectric effect, and another one is the uh, strictive magnetostrictive effect. Okay, uh, fine. So these are the effect, like in just I'm briefing that in piezoelectric effect, like there is a high frequencies transferred to the transducer, and that will start basically creates the amplitude. Okay, basically that will try to start the reciprocating motion. So this reciprocating motion, small amount of the reciprocating motion, we are calling it as a vibrations. Okay, so now there is it, and it is harmonic in motion. Okay, please please keep in mind that one. And the magnetostrictive is also the same. Here we are using the magnetic coils. Okay, so these two are the most important principle to in which we can we can transfer the high power electricity, and that will transfer into the reciprocating motion or the vibration, we can say. Okay, now the horn and the concentrator is used to amplify the vibrations to required amplitude to 15 to 50 micrometers. So whatever the amplitude that is in this range basically is needed, and if we will not use the horn, that this vibration is not this amplitude is not that much stored. If we will connect this transducer to the directly to the tool, then because it is a tool tip. Okay, because like generally it is used for the very small thickness, this principle this sorry this USM process is used for a very small removal of the material. Okay, cleaning purpose or deburring, like that. So if we are this is basically the tool tip. So now there will be no proper vibration if it is a very small. Then if it is directly connected, this tool is directly connected to the transducer, then the amount of the amplitude is not that much, because uh, that vibration is where it will transfer the amplitude, basically where it will transfer the vibration. Okay, there should be a larger, little bit larger, not that much, but little bit larger shape is required. Okay, so for that only we are using the horn. So here basically one thing I have forget to mention, that is here this is basically the horn, completely it is a horn. Okay, this is the step type horn, step type horn. Okay, because this is the different diameter and this is the different diameter. Okay, so this is the, now here I forget one thing is forgot, that is here I have to keep a tool tip as well. Okay, so that please keep in mind that one, that tool tip we are keeping at the end of this horn. Okay, where the amplitude is transferred. So when we will use this horn or the concentrator, that time this amplitude range in the range of 15 to 50, 15 to 50 micron. Okay, fine. So this is the working. I think it's clear to you guys. Now just I'm briefing that what are the these types of the horn that we are using. Okay, and what types of the horn and the power system, like if we are talking about the transducer and we are using the horn in that. Okay, so this is basically the transducer. Okay, which is connected to this power cables and the power amplifier or the signal controller, because electrical system is there. And this is like the this is the horn. Okay, so how basically it will vibrations, how it will vibrate. Okay, so if when you will transfer the signal through this to the transducer, okay, that will start vibrating. Okay, so it will basically, I'm just drawing a line. Okay, so it will be like it will start vibrations. Okay, like that. Okay, it will start vibrations. Okay, up to this, like this only. But we have to magnify this vibration. Okay, because we have to increase the amplitude, so that's why we are using the horn. Okay, now this horn, if we'll use the horn, then this vibrations will be increased, the amplitude of that vibration is increased, and it will be like that. Okay, this is the range. Okay, so this is the maximum vibrations. So means what like you can ask here one question, that why I kept over here only maximum. Okay, so this is like when we are making this horn, when we are machining this horn or manufacturing this horn, that time we are keeping this L by D ratio, this length to the diameter ratio. Now what we call this ratio, you have studied in the strength of material, that is a slenderness ratio. Okay, this is the slenderness ratio. So on the basis of that L by D ratio, we are making this, we are manufacturing these horn. Okay, so these horn are available in different types, like in, it can be used the step size, or we can use as a taper section, we can use as a like this taper, but it's like increasing the diameter. Okay, like this. Okay, so this is basically the this is basically the type of horn. Okay, so these are the three types are available. Okay, so this is like why it is maximum, because the according to the L by D ratio we are manufacturing. And like if we will not use this so okay, what is the L by D ratio, that will be less than, that should not be greater than 20. This is less than 20. Okay, so if it will be like if you are going beyond that, then it will happen that there may be a chances, like this can be a possibility that these vibrations can be of this one, this type. Okay, this red one. So here, like here we are getting the maximum vibration. Okay, we are getting the maximum vibration. So if you have to get an optimum value, that time what you have to do, you have to remove this portion from this horn. Okay, because if you will use this much length of this horn, then only you will it will give you the maximum amplitude. Okay, within that ultrasonic frequency. So I think it's clear to you guys. Okay, shall we move to the next? Okay. Okay, next is the modeling of material removal rate. Fine. So again, here are also some of the assumptions that we are assuming. So first is the tool vibrates, it leads to the indentation of the abrasive grids. Okay, uh, it leads to the indentation of the abrasive grids. Hence, primarily the material removes due to the indentation of the hard abrasive grid on the brittle material. The simple crack is initiated, then it will propagate. Okay. During this indentation, the crack propagates due to the increase in stress and ultimately leads to the brittle fracture. Okay. And other than the brittle failure, that is a solid to solid impact erosion. Erosion is against jet impinging over the workpiece surface, and that will remove the material. So here basically solid to solid impact. Okay, means abrasive particles to abrasive particles, and after at the contact of the workpiece, this abrasive particle will contact with to the workpiece. Okay, due to the free flowing impact of abrasive against the workpiece, and that is estimated, means that's okay, that means solid to solid impact apart from the brittle fracture. Okay, so this is the mechanism. Now what we assumed yesterday, that when this material when we are talking about the brittle material, then the material is removed, okay, from the workpiece, that is in the form of like whatever the material is removed, we can assume that that is removed in a semi spherical form. Okay, so now here is also we have to, this is the workpiece, here it is a workpiece. Okay, and whatever the material that has been removed, if this is, I am assuming that this is the from here to here, this is the radius, small r radius, then this small r radius will be throughout. Okay, this small r radius will be throughout. It means this is the basically the amount of the material that has been removed from the workpiece area. But here one more thing, then we'll start deriving this. Okay, let's first I'm just writing the formula, then I will explain that one. So what is the material removal rate? The material removal rate will be equal to how much amount of the material is removed per unit time. Now, like how much amount of the material, that is volume in case of the brittle material. Simply also we can write v, because v, because here it's not applicable for the ductile material, so v also we can represent, or vb is fine. Now in per unit time, so here is basically we are using the ultrasonic frequency, and this material removal rate should be calculated. We can calculate it for like one abrasive particle is impinging over the workpiece surface, then is for the another one, for third one, then fourth one, and we have to average. But here we can use this for the number of particles, so this will be like small, and that how many number of abrasive particles is coming in contact with the workpiece at the same frequency, because frequency range also, like once we have set, that will not be changed throughout the process, because it depends on the material, workpiece material, that what material we are using. Okay, so this is like vb into n into f. So now this is the volume. Okay, so this is the volume. So this volume will be equals to semi-spherical in nature, and the radius is small r. Okay, so that will be equals to 2 by 3 pi into r cube. Okay, so this is fine. So this material removal rate will be equals to 2 by 3 pi r cube into n into f. Okay, now what we can do is, as we are impinging the workpiece material, means as we are in this abrasive particle is vibrating over the workpiece surface. So because of the vibration, the indentation is occur, right? So if the indentation is occurs, then the indentation will be like this is basically the indentation. This is basically the indentation occur over. Okay, so now if we have to means we just have to generalize, because for different size of the abrasive particle there will be a different indentation, because okay, right, because for the same same frequency, same amplitude, for this, if we are using the same size of the abrasive grains, then the indentation will be same. But if we are using the different size of the abrasive particles, then the indentation for these as the size vary, the indentation will also be vary, but for the optimum value, up beyond that we cannot go. Okay, so like we have to generalize, we have to find out the generalized equation, so we can find out the relationship between r and the delta from here. Okay, so for that I'm using this triangle like how we done yesterday in the abrasive jet machining. This is the O point, this is A point, and this is B. Fine. Now here, like yesterday we discussed about that this is the what abrasive grids, so that we represented by the diameter dg, right? So here is like is the abrasive grids can be in random in size like this, okay, like this, or like anything can be of abrasive grids. So here is like is the that yesterday is like impingement means impact, okay, but here it's not an impact, here it's like very small amplitude is transferred, okay, very small amplitude, or it's like we can say a continuous effort kind of things. Okay, so that's why what we have to consider is how much diameter of this section of this grid, okay, how much diameter of this section of this grid, how much diameter of this section of this grid, and how much diameter of this section of this grid, because all these sections will come in contact with the workpiece surface at some places, and that will remove the material. Because like if I'm talking about this one, okay, like if I'm talking about this abrasive grid, okay, so like it has n number of the n number of this sharp edges, okay, so every sharp edge had its own diameter, because we are considering that that is abrasive grid grain is in abrasive particle is in spherical in nature. Okay, so this whatever the sharp edges are there, they have a number of different diameters. So here basically in this one, like if we are considering this one as a grid, so we are considering that all these diameter is same, all these diameter is same, okay, because all this will come in contact with this workpiece surface, and the diameter of this is dB, is represented by the dB, and we call this section, this is basically the complete diameter of the grid, but small section which is here, this green one, this one, okay, this one, this is basically we call it as a bulge, this is the bulge, okay, this is the bulge, and this diameter is represented by this small dB. Okay, and if you will see the diameter of the grid, then this is basically the diameter of the grid, abrasive grid, this is the dB. Now sorry, this is dg. Okay, so this is dg. Now we can just simply, there is an equation that dB is equals to mu into dg square. This is just from the heat and trial method, so please keep in mind this one. By the way, this is not that much important. Okay, we'll just convert that into after what is requirement. Okay, so mu, that is, it's not a friction coefficient, it's just a random variable. Okay, that is mu into dg square. Please keep in mind this is the diameter of the bulge, dia of bulge, and this is the dia of abrasive grid. Abrasive grid. Fine. Okay, so this is the concept. Now what we were deriving, we were finding out the relation between r and the delta indentation. Okay, so now from this triangle I'm doing here, so that will be easy to write MRR for there. Okay. So triangle OBA. Okay, so this is, I'm just using the Pythagoras rule. This is OA square, like how we done yesterday. Okay, this is OA square equals to OB square plus AB square. Okay, OA is how much? This is not the DG, this is the DB. Okay, so this is DB by 2, because DB is like complete, this is complete is DB, but we are using only half radius that. So this is DB by 2 whole square equals to OB is how much? This one is OB. So this complete is dB by 2, and this is delta indentation. Okay, so this is dB by 2 minus delta whole square plus AB. AB is how much? This is small r, so r square. Okay, so when you will open is dB square by 2 equals to a minus b square, that is dB square by 2 plus delta square minus 2 dB by 2 into delta plus r square. So this will be cancel out, this will be cancel out, and that will be like 0. delta square minus dB into delta plus r square. Is delta is very small and delta square will also become very small, so we are just neglecting that one. So from here r will be equals to root square dB into delta. Yesterday for the abrasive jet machining what we got, that is dg. Okay, अगर यहाँ पे भी अगर bulge का discussion नहीं होता then it was a dg only, but please keep in mind this is the bulge diameter. Okay, please keep in mind. Now you can just keep this, put this value of r over here in this formula mrr. So this material removal rate will be equals to 2 by 3 pi into r, that is dB into delta cube by 2, because 1 by 2 root square is there. Okay, into n into f, like. But in the question, basically if the question is there, then the bulk diameter is not given to you, or it can be, there's a possibility, because you can get it from dg over here. So you can either you can place this value of dB over here. So when you will place it, it will become like 2 by 3 pi into dB raised to 3 by 2, uh, dB raised to 3 by 2, so it will be mu into dg square raised to 3 by 2, and delta 3 by 2 into n into f. Okay, so this will be like uh, 2 by 3 pi into mu raised to 3 by 2, mu raised to 3 by 2 into dg cube. Okay, delta raised to 3 by 2 into n into f. Okay, so this is material removal rate. Please keep in mind this formula. Okay, you can write it in the into the your synopsis part. Okay, so this is the final material removal rate for the ultrasonic machining. Okay, so if you have any doubt, then you can ask me, because after that we are deriving this one of the two of the graphs between the material removal rate and dg, and material removal rate and the frequency. Okay, because that is important. If it is clear, then we move forward. Okay, fine, great, Soumya, thank you. So we are now we are just looking for the process parameters versus their effect. So process parameters are like here the frequency in the dg, that is grid diameter, and we are just looking the how the effect will be on the material removal rate. So like from this graph, this the values only like 2 by 3 and pi, that is constant. Okay, mu is again a constant, because if we are considering here that this bulge diameter is same for all the grids, then this mu value will also be same. Okay, so this is also same. Now how it is depending, and also I have considered that for the bulk material, for the brittle material, we have considered that there is a spherical in spherical means whatever the material is removed, that is in spherical nature, and we are considering the indentation that we are of a delta. Okay, so if we are considering that the abrasive grain size is constant, okay, this delta is constant, and we are working on a same frequency. Okay, that is the same frequency, then how it is depend on that mrr. If I am talking about this dg, then this mrr is directly proportional to the dg cube. Okay, means diameter of the grid size, cube root of that. Okay, so first if you will see the graph, then this is the dg, that is diameter of the abrasive grid, and this is material removal rate. So what will happen, like here, like if you will keep this one here, it will be 1. Okay, here you will take 2, it will become 8. Okay, here you will take 3, it will become 27. So it will be like in this, like this. Okay, it will be like this, means थोड़ा सा y direction की तरफ झुका होगा, like okay, not, it will not incline toward that side, it's not step it, it's basically steepest to toward that side. Okay, झुका हुआ नहीं रहेगा, but it will be a straight line. Okay, now if you will see this one, that okay, diameter जो आपका ये grid size है, if you are continuously increasing, then what will happen, this is the workpiece, and like this is the tool area. Okay, so if small size is there, then it's okay. If you are increasing the size, then okay, there is some limit is there, because if you will increase the size, then what the gap is required, then it will not remove the material from the workpiece. So in that case, the material removal rate will be decreases. Okay, so if that is decreases, so we have the optimum value of this dz After that it will start decreasing. Fine. So please keep in mind that if you are increasing the diameter of the grid, there will be optimum value. Up to that MRR will increases. Okay. After that it will start decreasing. Okay. Now, if you will see this formula, then DC is done. Now look at the F, that is the frequency. So how it will be affected? That is directly proportional. Okay. So MRR for the frequency. So like it is, it's like a power is to 1 only. So it will be like a straight line. It will be like a straight line. And here we cannot say this is the F and this is material removal rate. Here we cannot say that it will start decreasing after optimum value. The reason is like we have already decided that we are working in a ultrasonic range. We are using in a ultrasonic frequency range. We are using already we are working on a ultrasonic frequency range, and that is in the 19 to 25 kilohertz. Okay, so whatever the value that I'm taking from here to here, it is in the range of 19 to 25, sorry. Okay, so please keep in mind that one. If we'll go beyond that, then definitely there will be a decrease in the material removal rate, but that will not be the ultrasonic frequency. So that also you have to keep in mind, please. Okay. So this is the two effect that that was I was planning to show you. Okay, so this I was decided, sorry, not planning. Okay, so it's clear. Okay, because after that we are just looking three objective problems are there, then we will leave this session. Good, very good. So first the problem asked in the GATE examination in 1992 by in the mechanical engineering, that is in USM, the material removal rate would be okay, it was a fill in the blank with increasing mean diameter of the abrasive material. So the option will be increases, decreases, increase then it decreases, or decrease first and then increases. Which option it will be? Recently we have seen. Like, listen, if it is continuously increases, then means if it is increases or continuously increases, yeah, continuously increases we can say if there is no decreasing term along with that increasing. Okay, Abhi, Avi and Somya. Actually, here it is talking about the with increasing the mean grain diameter. Grain is nothing but it's like abrasive grit only. So recently we see na, that this is the abrasive grit. So if you are increasing this diameter, no doubt the material removal rate will be increases, but there will be an optimum value. After that, it will start decreasing. So if you will say it is increases continuously, then what will happen? The example that I told you, this is the workpiece and this is the tool. Okay, so what maximum value you can take abrasive grains of this size here is like this much, only this much you can use. Okay, if it will increases from this one to this one, then what will happen? It will not insert inside. Okay, it will not insert inside, and it will just try to come in contact with this material. Okay, like in this shape it will come in contact. So what will happen? This is the tool vibrates, no doubt the abrasive grain will also vibrate, and that will remove the material. But the comparison, if you will compare this one, the whatever the material rate was removed in this area, first this is the D1 diameter and this is D2 diameter, then the material removal rate in case of the D1 diameter is greater than in the material removal rate of the D2 diameter. Okay, so now the option will be, it's not A, it's not always increases, decreases cannot be possible, so B and D eliminated, so the option will be C. Now is it clear? Okay, good, very good. Okay, next is in ultrasonic machining process, the material removal rate will be higher for the material width. The question asked in the GATE examination two times in mechanical, 93 as well as in the 10. Okay, good. In the 10 and the 93. Okay, so ultrasonic machining, the material removal rate will be higher. First of all, just check for what material we are using. The ultrasonic machining is used for the brittle material where the hardness is more, or low toughness. Okay, because if there is a toughness, that complete energy will be consumed by the material. There will be no removal of the material. Okay, so if first let's see the these options. Higher toughness. If it is high toughness, then the energy storage capacity is also high, so that will not transfer the amplitude, whatever the small amplitude that is generated. So this option is cancelled. The high ductility, that is affiliated with the toughness only. Okay, before this one, just talk about this one. Let's high fracture strain. If there is a high fracture stress, fracture strain means that is the stored capacity. Okay, that how much it can store. Okay, so again, if it will be high, if there will be a high stress, high fracture stress or strain, then again we are talking about the toughness. Okay, so that will also, again this option will be eliminated. So only one option is remaining, that is low toughness. If there is a low toughness, it means that, in other terms, like, it's not exactly, but sometimes we can say that high hardness. High hardness. Okay, so the option will be C. Okay, all three are eliminated, one option is remaining. Fine. This is the last question. Okay, so in the ultrasonic machining machines used in the material removal rate processes require ultrasonic transducers. Okay, the transducers work on different working principle, right? Because we can say that what I told you, that is piezoelectric effect and magnetostrictive effect. Okay, so through which basically both is affiliated, in which we transfer the electricity, and that first piezoelectric, that will convert into the vibrations or the reciprocating motion. Magnetostrictive, that will take the electricity, and that will magnetic effect will be transformed, and that because of that the vibration is induced. Okay, so okay, that is, transducers are based on this different working principle. Okay, one of the working principle of such ultrasonic transducer is based on, fine, eddy current effect. Eddy current is not is used, eddy current effect is not transfer is not eddy current effect. Basically eddy currents are not used to transfer the vibrations, that is just to show the effect, means magnetic effects or the electric effects, we can say. Okay, electric effects, so this is eliminated. Seebeck effect is like it's like a thermo effect. Okay, means how the temperature variation is transferred to the voltage or EMF, we can say. Okay, so this is also eliminated. Piezoresistive is also like it's like a piezoelectric effect, but the more effect, means it, when you will transfer the electricity, it will not exactly vibrates, it will transfer this complete heat energy to the to generate the voltage or the EMF. Okay, so this is also eliminated, only option D is remaining. Okay, so that is option D. Yeah, piezoelectric effect, Abhi, very good. So in this process, this is all from my side. Thank you so much, guys, for joining this session. If you have any doubt, you can ask me. It's clear. Then we end the session, and tomorrow we will discuss about the EBM and LBM process. Okay. Hopefully, I will try to cover it by tomorrow. Tomorrow itself. And if something will be remaining, then we will take one more class. Okay. Yeah. Good day. Have a good day and good night, dear. Take care. Bye bye. Take care.